Chile is going to present in the seminar. It's going to be great. Let me just remind you that to subscribe to the seminar mailing list, I'm going to send instructions on the chat. You send the word webinar to our email, geodiff@unicamp.br, or to this WhatsApp number, and you will be added to a WhatsApp list and or to a mailing list, an email list, strictly committed to advertising the seminar, or maybe the occasional immediately relevant conference in the future when there will be conferences, right? But that's that. Please subscribe so we can keep you up to date with the calendar. So just remind you as well that our seminar runs alternatingly with a fortnightly frequency between Thursdays and Fridays. So this week we're having it on a Thursday, which means that next week it's going to be on a Friday. There's a seminar every week planned. Also, if you'd like to appoint some speaker, you can let the organizers know by those same channels. So if you'd like to see someone speak, the only requirement is that that researcher is either South American or works in South America, like a Mircea, who's European, but is working in Chile. Okay, so if you have any suggestions, people you'd like to see, let us know. So without further ado, let's welcome Mircea Petrache from Católica de Chile, telling us about uniform measures of dimension 1.
Okay, thank you very much for the opportunity to talk in this seminar. So I'm going to tell you about some common project with Paul Laurent from Paris 7. And it's about uniform measures. So let's see what is a uniform measure. And so basically, suppose we are in a metric space, and then about a random measure, a positive measure on this space, we are requiring that it is uniformly distributed or uniform when we require that for all radius and for all points in the support of the measure, the measure assigns equal mass to balls centered at these 2 points with the same radius, right? So in other words, the measure doesn't really distinguish some point in its support if the only information you have is the measure of balls of radius, of arbitrary radius near that ball. So the points are all looking the same. The distribution around, radial distribution around the point is the same for all points. Okay, and so a case where this automatically happens is that, hello? Everybody is muted. That's why I stopped listening. Okay, so
we can hear you. That's fine.
Yeah, very good. So a case where a measure is uniform is if I have an isometry of my space that interchanges any 2 points in the support of the measure while keeping the measure fixed. Yeah, and so then automatically this will be equal to this because there is an isometry moving the measure to itself and one ball to the other ball, right? And this is, in this case, if everything is explained by a subgroup of the isometries, the measure is called homogeneous. And in fact, the thing is that not all uniform measures are homogeneous, it turns out, and this makes the topic a bit interesting, and kind of the question of classification of uniform measures becomes pretty hard and pretty interesting to find counterexamples to, or like to find non-homogeneous uniform measures. And I mean, at the same time, while this is true, it's also true, like, let's make a drawing here. Suppose that I have a measure that is just, I represent the density by these lines. And then what I can have is like, So suppose I am looking at the big ball of radius r, then I know that the measure contained in this ball, the total mass of this ball, is some function f of r. But at the same time, I can cover the measure by balls center inside this big ball, right? And so there is a relation between f of big R and f of small r. In some sense, being uniform constrains it a lot, because all balls of larger mass have some relation with balls of smaller mass. So they are at the same time quite rigid clasps, right? Okay. So due to the fact that this theory doesn't have so many results and it's kind of hard, I'm going to consider only measures in Euclidean space. So my metric space is going to be Euclidean space. I have to tell you that there are some results. There are general results in metric spaces, but if you are just working in all the possible metric spaces at once, then you don't go so far in the classification, yeah, let's say. On the other side, if you have space, you are looking at a specific space that is not RD, then you have basically no theory. Just recently has started to grow some theory of uniform measures in the Heisenberg groups, right? So the Heisenberg groups are you take R to the 2n plus 1, and then you have an n-plane non-integrable distribution of planes, and in order to join one point to another, you cannot do straight geodesics. You need to have geodesics that are always tangent to this plane distribution. So the outcome is that you need kind of a long way to go in order to join nearby points that are not kind of parallel to this plane distribution, right? So you have a metric space which is essentially different than RD, and is the first space essentially different from RD, the simplest kind of model space that people study. So in that case, especially when you have Heisenberg group of dimension 1, then there are some results and some classification there. But everything follows a bit the tracks given by the Euclidean space setup, right? So we are just restricting to that, right, for this talk. And then the main motivation of this, the main motivation is a study of rectifiability, yeah, and the study of the so-called geometry of measures. So we are looking for general measures in RD, and you want to know to study the structure of these measures, which is like a classical kind of motivation, but at the same time, you can think that in our big data world is quite close to the questions that one needs to answer. So for example, you want to know how in a space where you don't know much, you just know what distribution of points, which can be represented by a measure. So you want this distribution of points to study its structure, what to look at in terms of the distribution of points in order to classify and find some geometric structure of this. For example, this can happen if you want to study the geometry of manifold learning, so-called manifold learning, you end up with questions that if you are abstract-minded, you transform it in question about the geometry of measures. Okay, so what is this original motivation? Just to be precise and to have one important theorem. This is the basic theorem at the base of geometric measure theory. It's a long paper by Preiss in, I think, in Acta Mathematica, 100 and something pages. So basically, the result is this. It's pretty general. You say, I have a positive, locally finite measure, and suppose there is a number, positive number, such that this limit density exists. So that if I look at smaller and smaller balls, yeah, have R smaller than going to 0, and then the density of balls is comparable to R. The measure of these balls are comparable to R to the alpha. So if this happens, and this comparison is away from 0 and away from infinity, then you get several informations, a bit surprising at first. So the informations are that alpha will be an integer. This is a strong one. And then also the mu will be actually the Hausdorff measure, actually a density times the Hausdorff measure of that dimension restricted to a rectifiable set. So a rectifiable set is some set which has tangent planes of dimension alpha in a weak sense. Okay, so you are intersecting your set with balls, and the intersection is the smaller the ball is the closer your set is to look like a plane from the measure theoretic sense. Okay, so you get a lot of structure just for knowing some control density of the measure, right? And then this is the final result of a long series of works that started actually at the beginning of the 19th century, of the 20th century, with Bezikovich. Bezikovich studied the case of alpha equals 1, so one-dimensional measures in two-dimensional space. Then there was Moore, who ended up who generalized this to dimension D for alpha equal 1. Then the one big step forward was the work of Marstrand, who proved that alpha is an integer. And then this paper of Preiss actually wraps up everything and introducing several new techniques that are still not completely. I mean, they weren't brought to their final potential. There are some things to get mined in this paper of Preiss. Okay, for me, how I got excited about this was by looking at these books of the books of Mattila and the Lellis, especially this one where it was formulating some open problems, okay, which are basically describing a subset of the work of Preiss in this case, and describing the whole story, but without entering into too much details about the work of Preiss in this other book. Okay, and actually, just maybe one thing that if you look carefully in the work of Preiss, actually the statement is more complicated, right? So, but it's a bit weaker. So the assumption is a bit weaker. So actually, it's enough that the density, the limb sup, when I take balls, smaller and smaller balls, the limb sup of the quotient with R alpha of the measure of a ball of radius R doesn't need to be equal to the limb inf, but needs to be not so far from the limb inf, right? So there is a constant, so that if you have a gap between the limb sup and limb inf not bigger than this constant factor, then you still have the same information as before. So it gives you the information. If you look at this kind of like that abstractly without entering the details, it tells you that actually maybe there is a discrete discrete kind of organization among what are possible blow-ups of measures, possible infinitesimal structure of measures. So if you are not too far, not oscillating too far as the radius goes to 0, then you still get the same information as if you have a limit, right? So that's the first indication that some geometry is going on and in the classification of tangent spaces of measures. Anyway, so why is it so important? Why uniform measures are at the center of the study of rectifiability? Well, I'm not going to try to convince you in detail. I just give you from a kind of motivation looking from far away, right? So if you look at the table of contents of this very important paper giving the main structure theory for measures that we know at the moment, you imagine something like that you have some preliminaries, and then you get a study of what you look at. You want to show that the measures are supported on a set with tangent spaces, so you want to talk about tangent measures, and then find out tangent spaces, so find out about rectifiability, and connect rectifiability notions to notions about densities, right? So that would be what you would like. Instead, Preiss goes on and on about uniformly distributed measures, so our kind of uniform measures, and approximately uniform measures. So it has more than half of, like maybe more than 1/3 of the paper talking about this theory of uniform measures, right? So it's really an important concept in order to organize information about the geometry of measure, to organize in your mind your information based on a model of a very kind of, well, uniform measure that look everywhere the same. Okay, so that's all about information from geometric measure theory. And where I start to look at this is at this question from Preiss, right? So he's saying, I'm going to read it. This is at the end of the part about uniform measure. It says, it's not difficult to give a description of uniform measures in R. Yeah, these are the uniform measures on the real line. And uniform measures in R2 such that the support of the measure is bounded. And for this, he says, see this paper. And then to give a similar description of uniformly distributed measure in higher dimensional space is a natural, though probably hopeless question, right? It's a pretty depressing end of this chapter about uniform measures in this paper. Well, so let's look at the hopeless question, right? So here are the known facts that we have related to the theory of rectifiability, right? So this is the part where the kind of question you get if you are interested about tangent spaces of measures are this. So you always try, in the end, if you are caring about rectifiability, you care about measures that are just going like an integer power, right? That the measure of a ball is the same as a constant times an integer, which is the same as the Lebesgue measure of a ball times a constant in a plane of dimension m. Okay. So first of all, if you have a measure that is uniform but also dilation invariant, then it is of this kind. It has this distribution function, which is just a simple power. But it doesn't need to be the measure restricted to a plane. So basically, this is the main example of a strange uniform measure, right? So basically, what you have here, you are in R4, and you look at the cone which has a right angle at the tip, right? So you have the first 3 coordinates squared equal to the last coordinate squared. It's what you call a light cone if you have a Minkowski metric. But I mean, here is just a cone in R4. And then what you can do, you can imagine. So let's say I imagine my cone. Here it has an S2. Yeah, it's a cone over S2. And then you take a point here, you intersect the cone with a ball in the ambient space. And then what you find is that it doesn't matter where on the cone you put your center, you always get the same measure. So the surface of the part of the surface of the cone that is contained in this ball is always the same, no matter where you put the center. So if you put the center and it goes to infinity, then the cone becomes flatter and flatter. And then you get that actually, the value, this number here, is the same as the Lebesgue measure of a ball in R3. Yeah. So you get that actually this cone is undistinguishable from a plane. It can you are just if the only thing you do is you intersect balls centered on the cone and see how much surface is in there. And in fact, it turns out that as I say in the next point, so the uniform measures which have a distribution which is just going like the power of the radius to the d-1, and then this can be only 2 things: only a plane or this cone multiplied by a correct dimensional plane, right? So
Mircea, can I ask you a question?
Yeah, sure.
So there doesn't seem to be anything sort of dimension specific to this, right? A cone, yeah. I mean, morally, a cone looks locally like a plane, sort of just in general. Yeah. So what am I missing here? What's specific about the dimension?
But I mean, this is everybody would like to know the answer to this question, of course. So basically, the main thing, it's actually what you say, a cone is very similar to a plane. That's not true. I mean, imagine if I have a ball center really here in the center of the cone, okay, then it's going to have a surface which for some aperture of the cone, it's always the same as for a radius, but for a plane. But if I look at a point that is a bit kind of asymmetric, you have a ball that is a bit asymmetric, it doesn't need to keep exactly the same measure wherever I move the center, keeping the radius fixed. So it's kind of very astonishing for me. I mean, and then actually this is based on the fact that if I have S2, and then I can have a similar property. So I intersect S2, I take a point on S2, and I look how much surface is contained in a ball of radius R. Well, this is the same surface that would be contained in a ball of radius R in R2. And then you can think this cone is just many S2s put together, one after the other, and then you integrate, you split your integral in a correct way with part of integral over S2 and then a second integration over the other direction. And you find that it's a kind of algebraic calculation that doesn't give you information about the principle. And so that's a bit why these are so hard to classify, because that's the thing that we know. And then
okay, but why is the dimension relevant? It's just because there's some
this doesn't
Jacobian
happen
in this integral that
for S3 doesn't happen this. So
okay,
I don't know. It's an algebraic thing, really. It's not really. It's just about the algebra of the numbers that come up. It's not. I cannot tell you with a nice explanation why.
Okay.
We don't have a nice explanation. That's why it's interesting.
Yeah. Okay.
And so this is the kind of thing that we know. We know that at least if you have codimension 1, then these are all the examples, so that you can get that have a distribution like the power r to the d minus 1. And then another thing that we have, and we are going to see it later, we have that if I have a uniform measure, then it is constant times the area measure of an analytic variety, right? The analytic varieties, unfortunately, there are many of them. Most of them, they don't give you uniform measures, but at least you know some regularity of this measure, right? So you know that it's really like a nice manifold, at least locally. And then this paper is kind of funny. I mean, I write here a bit something funny, that it was published kind of more than 10 years later because of Cold War reasons, right? So this paper here is the same paper cited in this paper in '87. It's is this paper that was published much later, but it's very nice. It's we are going to see a proof of this result that it's an analytic variety just in a while. And then more recently, again, related to study of rectifiability, there were results by Dali Nimmer, who is now a postdoc in Chicago. And he was a student of Tatiana Toro, geometric measure theory. He was proving that the singular set of this analytic variety, the singular set must have dimension at most k minus 3, right? So if I have a measure of that has distribution r to the k, then the singular set is at it has codimension the same as in this cone C3 or lower, right? So he proves this regularity result, and then he also proves that for measures that go like r to the 3, then you can have not only a cone over a sphere, but a cone of a collection of tangent spheres that really span the space of any dimension d. So you have d minus 4 tangent spheres in a kind of generic but very special kind of position in d minus 4. There are d minus 4 of them, and their centers are positioned in space of dimension. Let me think of dimension d minus 3. Right, in a space of dimension d minus 3, there are these S2s of different radii. Then you take the cone over them, and it gives you again another kind of singular cone, which is undistinguishable from a plane. Then you can take the product of that with the hyperplane to get more examples. But so
sorry,
far,
can I just understand the statement? So is it say if I take k equals 2, so if balls measure sort of quadratically, then does it mean that the measure is always smooth, so that it's non-singular?
So yeah, this would be a consequence of this. That the singular part, so it's a smooth manifold away from points. In that case, it would be yeah. So if you are of dimension 2, then you would be regular. And if you know this, that here you don't have any function, you don't have an arbitrary function, but you have really a power.
Squared in this case. So if it's squared, in particular, if it's squared.
Yes.
Okay, that's
but nobody.
We only learned this in 2015. That's impressive. Seems like a very basic state. The first thing you would ask about the measure, right? And then
yeah, but I mean, I think this could be a bit the consequence of putting this word here. This thing, when you present an open problem as probably hopeless, then people don't work on it too much. I think that could be related to that. So it's not. I think it's not really that hopeless, although it's not obvious how to solve it.
Okay.
Yeah. So these are the results. This is all we know. This all the how much it has advanced for the case that we have a power, that the measure of a ball is going like in Euclidean space of dimension k. And then let's look at more general case. Now we go away from this rectifiable case and just look at the problem maybe from a bit different light. So I'm going to give a name to this distribution function. So we have the same definition of a uniform measure. And this says that for all centers in the support, I have this function that tells me how much is the measure of ball of this center and radius r. And the function depends only on r. And so now I can think, let's try to see what do we know about the form of f and the form of the measure mu. What kind of functions and kinds of measures do we know that this can be? What are the restrictions? So the first thing, which is a compound of several results, very heavy machinery results from geometric measure theory. Well, they they only care about rectifiability in the end, but the result that you can still get from that as a fast corollary from their work is that this function is an integer power and then lower order terms, right? So the leading order is an integer power, at least, of this function f. And also the measure mu is rectifiable. I mean, so when you know some information about f, it also kind of hides some information about the mu. Okay, so we know that the measure is rectifiable, and this implies that f has leading order an integer power. But in fact, we have this other result, which I already mentioned before, which is saying that actually there exists an analytic k-dimensional variety v, and the mu is just the area measure of this variety times a constant. And so it means that f is also analytic on a small interval, at least, right? It's so imagine the case of a sphere. If I have a sphere S2 and I put a point on a sphere, then for radius smaller or equal than the diameter of the sphere, this f will be analytic, and then it becomes constant, right? So it stops being analytic. That's a bit the idea of this formulation. Okay, but the main information is that the measure mu is the area restricted to an analytic variety, the area measure of an analytic variety. So this is this theorem actually allows us to now use differential geometry tools in order to study these measures. We just study what kind of varieties can have a uniform measure supported on them. So let's look at the proof. The proof is, I find it's a very elegant result because it seems like it's giving you a lot of information at once. So the result is, first, you are using this covering theorem, say by how many balls of radius small r can you cover a ball of radius big R? Well, this is something that depends on the quotient of r, big R over small r, and of the dimension. And So using this bound, you find that the function, the measure of a ball of radius r, no matter where you put its center, on the support of mu or somewhere else, well, it's bounded by f of r times the power factor to some power which is equal to the dimension, right? So it tells you that the distribution function f is also not growing more than a power. And then this allows you to, so all the integrals that you end up finding, you can use this growth control of f. You control the growth of f, and you can bound your convergence of your integrals. So now let's test the measure mu against the Gaussian distribution centered at a point on the support of mu. Again, any radial function can be decomposed as a superposition of characteristic functions of balls. So I'll just imagine my Gaussians split up into level sets, and then I am going to change variable and express everything in terms of this distribution function f. And it tells me that basically, again, the Gaussian, if I integrate the Gaussian on a measure, this integral doesn't depend of the choice of point in the support of mu. And now let's take another point. This is a general point, not necessarily in the support of mu. X is in Rd. So I take x in Rd, and I integrate a Gaussian centered at x minus my previous Gaussian centered at a point in the support of mu. Yep. And what can happen? Well, first of all, because of this growth condition here, I can find that this integral converges nicely, and that I find that this is analytic in x. Yeah. So this is because I'm integrating analytic functions, and the convergence is fine enough so that the power series that defines my analytic function is still working. And then the second thing is that imagine what is going on. So here I have my measure mu. I look at the Gaussian here, and then I look at the Gaussian. So this is at the point x0, and here is centered at the point x. Well, the Gaussian centered at x0 will always be given has a more interaction with the measure mu than the Gaussian centered outside the support of the measure, right? So this function is the f is lower, is smaller or equal than 0, and is equal to 0 exactly when the point x is on the support of the measure. Okay, for all s. Only if for all s the point is in the support of the measure. So my support of my measure is the 0 set of some analytic function. So it is an analytic variety. So this is how we prove that it's the measure is supported on an analytic variety. And now we have to prove that it's a constant multiple of the measure of this variety. So to do that, I'm going to use the differentiation of measures. So I look at the measure of a ball, and then I divide by measure of the ball plus the area measure on my variety applied to that ball. Okay.
Can I just ask you? What happened to D, right? So on the Besikovich bound, what happened to D? Does it just vanish when you do the Jacobian for the radial sort of polar coordinates?
No. So this is actually the thing we are going here. We are writing using the Cavalieri principle. This is I said it's a change of variables, but in fact I am just reordering the integral. And I just say that the exponential is a superposition of characteristic function of balls.
Okay.
And then
right, but how does f come into play? What happens to r over r to the power d?
So here I would have r to the d minus 1 dr, and then I have this r to the d from here, so they cancel in a way. I mean,
right. So that's what I was asking. I see. So it cancels when you do the polar coordinates thing.
In some ways, yes.
All right. Okay. Good. Okay. So I understand. Okay.
Okay. Yeah. And then so here, coming back here, I have that this measure mu is independent. The mu of BR is just f of r, and the hk of restricted to the support is very well approximated. I mean, asymptotically equal to alpha k rk, where alpha k is the measure of a k-dimensional unit ball. And so this number is going to a constant, and from that it follows that also this the limit of f of r divided r to the k is going to a constant. So in other words, it tells me that my measure is this constant times the area measure of the support of mu, which was an analytic variety, right? So we have basically, this is the whole reason why we restrict to integrating area measure of analytic varieties. Yeah, so now from now on we can go on and do differential geometry on our varieties to see what could they be if their area measure is uniform. And so we do this differential geometry algorithm, and we can start by saying actually mu is locally a submanifold, and we can also say that it is an analytic submanifold, so it has you can do all the Taylor expansions you want without being punished. And then let's do it. So basically what you do, you parameterize your submanifold. So I have here my submanifold, and I look at it as if it were a graph over its tangent space, for example. And then I take a ball of radius r, and using the parametrization, I can write the Taylor expansion of the number, which is how much. Okay, so suppose here we are having coordinate center at the origin. So the origin is in my submanifold M. And then, so I have a Taylor series. I can express my intersection of a ball with my manifold as a Taylor series in R, right? And then I know that the coefficients of this Taylor series need to be all independent of the choice of the point of my manifold where I'm doing my parametrization, right? So these have a geometric meaning, these coefficients in this Taylor series. So what one has a geometric invariance of my surfaces, and I want to find ways that the coefficients in this Taylor series are encoding information about geometric invariance about my variety. Okay, so this is the hard part. Yeah, that's to look at these coefficients in the Taylor series and show that, for example, you have some curvatures, a relation about curvatures, or other invariants. So this is hard, the hard part. And then also hard would be, but this you will see we didn't do it. You could look what happens not at r going to 0, but at r going to infinity, right? So that's another case where you can have an analog of a Taylor expansion. Okay, so basically the work which led to the classification and to discovering this tangent cone. No, not a tangent cone, light cone. This what I call C3. This was based applying all these steps and looking at Taylor expansions up to degree 4. And then our work was, let's look at measures of dimension 1 and just go with the Taylor expansion as far as you want. I mean, as far as you need. And it turns out that we needed up to 2D terms, right? Something up to 2D term. So basically, out of this, I'm going to tell you this part, what is our result about one-dimensional uniform measures. So basically what we have is, first result is this. So suppose that mu is the 1D, the length, mu measures the length of a curve in RD. Okay, so we suppose that we forget about other possible cases. We just look at mu, which is the length of the curve, which just measures the length of the curve. And then we found that actually being uniformly distributed is the same as being homogeneous, right? So we don't have any surprise counterexample in that case. And then what are homogeneous measures? Well, it means that all the curvatures of my gamma are constant. So you know that you have a curvature, torsion, and higher order curvatures if you are in high enough dimension. And so you have in total d curvatures that characterize your measure, and they are all constant, okay? So we find that actually that gamma needs to be a toric knot or a generalized helix. And then, of course, not all, you can have all the generalized helices, which are uniform measures, but a toric knot, you will have a toric knot of a special type, the one that doesn't become dense in a torus, right? So toric knots could have an irrational angle. That ones we don't have, but if it has kind of a rational angle that it closes itself after finitely many loops, then this is fine, because mu will be locally finite in that case. Okay, so this is what, so there is no surprise there, and this was the case where gamma is only a curve. So you can imagine you have a helix or a toric knot, which is like a helix closing up over itself and sitting on a torus. And then what we find, what about more general uniform measures of dimension 1? Well, then connected components form a discrete set and are all congruent to each other. And then the other thing is that if these are helices, then the helices are translations of each other, right? So you can imagine here that you have like a field of grass, and each one of these plants growing on your field is one helix, right? So all the helices are parallel to each other, and the whole information left is to know what are the different translations that relate all these helices. And so the translations correspond to a uniform measure of dimension 0, right? You will have a uniform measure of dimension 0 in the correct dimensional plane. And unfortunately, uniform measures of dimension 0 are not classified, right? So we know that lattices are uniform measures of dimension 0. And we know some other examples, finite many copies of lattices put in a very symmetric way. But we don't know any, for example, non-homogeneous zero-dimensional measures. So kind of some point configuration where all the distance, all the number of points at the given distance is the same whenever I choose one center inside this set. But these are not classified. So that's why we cannot classify completely uniform measures of dimension 1, right? Because we just know what the connected components are, but not how they are positioned with respect to each other. Okay, so if I have enough time, yeah, I have some time, right? Then I could go to show you a little bit of the proof of this part.
Sure, you have just over 10 minutes. Yeah, let's do that.
So what I'm going to tell you basically, in our case, how do we do this? Well, not all this, but the first 3 points, right? Which is I'm going to explain to you why these points 1, 2, 3 can work, and what is the kind of little trick that we have. Okay? Here, the goal actually the goal would be to find to kind of gain a bit more insight and a kind of statistics of what can be going on, so that we can do, for example, uniform measure of dimension 2 in R4, and then dimension 2 in R4. It's still not clear if there is enough rigidity or not enough rigidity that you can have a smooth, non-homogeneous uniform measures, or still they are all homogeneous, right? All coming from a subgroup of isometries. Okay, so anyway, in dimension 1. So what we do is we start saying our curve, we are looking at the curve, and the curve is analytic. this is coming from this result about a measure being a multiple of the area of an analytic variety. But if it's dimension 1, then it's the length of the curve, which is an analytic curve. And then we use an old result by Nomitsu. So there was in the during the half of the last century, there was a lot of study of Frenet frames, and then Nomitsu was showing that if I have an analytic curve, then you can subdivide it in segments, and in each segment, the dimension of the Frenet frame. So kind of basically the Frenet frame is given by all the derivatives, the successive derivatives of my function, renormalized, and then after a while, if this function has some curvature that is vanishing, some kind of torsion, of higher dimensional torsion that is vanishing, then this curve is going to be included in a plane, in a higher non-zero codimension plane, right? If some curvature vanishes. And then he showed that actually you can do the part of the Frenet frame corresponding to the non-vanishing curvatures, define it in such a way that so basically I can divide my curve into intervals, and in each interval I can have a frame, yeah, a frame. I can define uniquely a frame field. So I fix the frame at the beginning, and there is a unique continuation of my frame field, at least interval-wise, yeah? And then maybe here there will be a kind of a degenerate point, and then I have to start again and keep rotating my Frenet frame field, and it's uniquely defined by the value at the extreme of the interval, right? So it's locally non-degenerate in this sense, that you can find a unique Frenet frames continuation along the curve. And with these results, then we start with the Taylor expansions, right? So we express first we will parameterize our curve by arc length. So we are supposing that the tangent vector is unitary. So basically, the first term in the Taylor expansion of my curve is going to be given by a unit vector times t. And then I have some other vectors related to the derivatives of phi, of gamma, times the correct power of t. So this is a Taylor expansion in t of gamma. And then I'm going to take this Taylor expansion and plug it in order to get a Taylor expansion for the distance of a point to the origin. So this is the distance of gamma t to the origin. And then it has the first coefficient 1. And then the others are just expressed in terms of the scalar products of these coefficients in the Taylor expansion of gamma. And then we solve this equation. We try to solve, and then we manage, because this coefficient is 1, we manage to find the solution of gamma of f equal R2, right? So this is giving us, so I have my curve here, and then I take a ball, and I intersect with a ball of radius r, and I'm trying to look which are the parameter values at which the curve intersects. So we can find solutions of this just by formal inversion of the power series. Yeah. So we have a power series here, and then by a formal inversion we have this, and the formal inversion is okay because we are in an analytic setting. And then it turns out, because the curve is parameterized by arc length, then we just have to subtract one arc length from the other arc, one parameter value to the other parameter value, and it gives you the length of the intersection of the curve with a ball. Okay, so we know, so this, you see here we have a Taylor expansion, and we know that the coefficients of this Taylor expansion, not all the coefficients, it turns out that the one with the even index are canceling out, and the others keep the same. Yeah. So we have odd coefficients in this Taylor expansion, which have
Why?
so you can find it algebraically, but you can also. So I remember at a certain point I was rationalizing it, saying that if I take my curve and revert the parameter, then it should be the same curve. But I think I'm not. I don't have. I couldn't build again a clear explanation from this. But when you solve this equation, you can solve the coefficients, and you see that the coefficients of the solution, which are explicit, are going to have the C plus 2 is equal to C minus 2.
It's something you can check, but it's far from obvious. I don't see why this should be the case, but that's very interesting. But it's not obvious, is it?
Yeah. Well, it wasn't obvious to me when I was preparing the slides.
Right.
So it was obvious when I first think about it. It was obvious, but it is this happens, right? So that just the odd coefficients appear.
Right.
Yeah. Okay. And then and so here you would have a power if you write it down. In any case, they cancel. This is a curiosity, but I mean, then in any case, you can write down a power series expansion for this. And now we have to relate these coefficients to the curvatures coming from the Frenet theory, right? So we have first of all, to start with, we have this. So AK is coming from a Taylor expansion. We know how the coefficient it related to the derivatives of the curve. So this is the kth derivative of the gamma at 0. And then a Frenet frame is just the Gram-Schmidt orthogonalization of the first d derivatives of my curve. Under the condition of non-degeneracy, which we are having at least locally, we have it from Nomitsu, right? So we have this Wronskian is non-zero, and then we can orthogonalize the Frenet frame, the frame given by the derivatives of gamma, and gives us the Frenet frame. And then we can define the curvatures like this. This is one of many ways to define them. As the derivative of Ej, a product scalar product with Ej plus 1. Okay, so we have this definition of what are, so K1 would be the curvature, K2 would be the torsion, and then we have higher dimensional curvatures. Okay, so now the goal is to connect the values of these curvatures with the coefficients from here, right? Because we know that this f of r is independent of the choice of the center along the curve. And this, if we know that from these coefficients of f of r, we can invert in some sense of a polynomial relation and obtain curvatures, then the curvatures will also be constant along the curve. So this is what we check. This is the thing that is not obvious, but one checks. Okay, so let's see how to show that K1 is constant, right? So I have a K1 of 0, by definition, is E1 prime of 0, and then E2 of 0, yeah? And then if you write it down, this is, so here E1 is actually gamma prime, right? E1 is just we say that our gamma is parameterized by arc length, and so E1 is equal to gamma prime, and so here we get something like gamma prime prime, and then gamma prime prime, something like that. And so it's equal to 4 A2 squared, right? So the A2 is just related to the derivative of gamma at 0 by because by the expression of the Taylor expansion, right? This was the second coefficient in the Taylor expansion. So this is K1 in terms of the coefficients A. And then another thing you can do is that you are looking at gamma prime of x. This is again equal to 1. So you get that gamma prime x, gamma 3x, third derivative, is actually minus gamma second x squared. Yeah, this is a consequence of taking two derivatives of this of the constant length parametrization, and then so this gives us that A1 times A3 is equal to let's see, A1 times A3 would be gamma prime of 0, and then A3 is equal to gamma 3 at 0 over 6. And then basically then you look at the coefficient. So you look at C4, right? C4 is equal to A2 squared plus 2 times A1, A3. Yeah. And then you find out that this is actually minus, this is minus 4A2 squared. So this is minus 1/12, I think, K1 of 0. Right? So you basically use all of this in order to express C4 in terms of K1 of 0. And then you notice that the other thing to note, so this is the first ingredient, and the second ingredient is that if I take the little ck's, which have a plus minus here, I mean, but the little ck's, let's see, ck plus minus ck minus, and I call this ck. Then this, the set of these for all the different k allows to completely determine the set of the big ck's. Yeah, so there is an algebraic, a non-degenerate relation here, so that it can be inverted. So if I know all the ck's, then I know all the big ck's, right? And then it tells me, because these coefficients of f of r, these are constant, so the ck's are constant, and so in particular k1 is constant, right? So this is how you show that the first curvature is constant. You just kind of chase the coefficients and find an expression of the curvature in terms of the coefficients of your Taylor expansion of f of r. Okay. So this is the simple case, and then you go on by induction, right? So far we know that all these ck's are the coefficients of my of the distance to the origin of gamma t. The coefficients of these are constant, and then I want to show that the curvatures are constant. So I know that first curvature is constant. So now suppose that the first h curvatures are constant. How I prove that the next one is constant? So here is the thing that we find. We find that c plus minus k is actually a polynomial of all the ck's, the big ck's from before, with the same up to from 2 to k. And then I have the ck plus 1 with the non-zero coefficients in front, right? So so this is giving me a way to determine the big ck's from the small ck's, right? So the big ck's are completely determined by the small ck's inductively using this.
Maybe we can be a little bit more sketchy just because of the time.
Ah, yes.
Yeah.
Oh, okay. So let me just skip so that we have all the things written down, and then
yes, great.
So basically, here is then I write the ck's in terms of the ak's, and then it gives me actually the same relation from before of h is actually related to the h derivative of gamma, and so I have Cj is a polynomial in the derivatives in gamma, and then the derivative of gamma, I can write it as a polynomial of the derivatives of the Frenet frame and the derivatives of the curvatures. And then I can, in fact, every time I have a derivative of the Frenet frame, I use this relation here, which is the Frenet-Serret relation, and I can lower the number of derivatives of E, and then split the, so say I have a derivative on E2, then a derivative on E2 is equal to minus K1 times the derivative of E1, times E1 without derivative, plus K2 times E3 without derivative, right? So I can, every time I have an E, I can split using this graph, I can split the contribution of derivatives on the E's as curvatures and derivatives on other E's. And so using the fact that the EJs are orthonormal, I can follow all the dependence of derivatives, and I can find that the coefficient C2H plus 2 is actually a polynomial on these curvatures, and these are constant. And then the term where the next curvature appears is precisely is non-trivial, is non-zero. So it allows me from the C case to obtain the K case, and inductively prove that they are all constant. So that's all. That's basically, I hope it was a bit clear how it proceeds.
All right, thanks.
Okay, sorry.
Thank you.
The clapping on a webinar is definitely a special experience.
Yes, it is. Thanks.
Can we do we have any questions for Mircea? Because I do. So okay, so let me ask my questions. So you mentioned in the beginning sort of two leads, which seemed interesting to me. First of all, you mentioned the work that's been done on the Heisenberg group.
Yes.
Sort of when you have this sort of contact structure, right? So you have a non-integrable distribution, and then distances have to be, your geodesics have to be tangent to this.
Yes, that's right.
Is this something that makes sense in the context of contact manifolds in general, or just?
I think so. I mean, what I understand is that I didn't go into details into the whole proof that they have, but what seems to follow is that the Heisenberg space is more rigid than the. So in n equal 1, you are looking at R3, and then you have a two-plane distribution which is non-integrable, right? So it turns out that if I have a point and then I have this point in the plane distribution, kind of the curve has to do, instead of taking this distance here, it takes a longer distance, which goes, so if this is epsilon, this is like square root of epsilon. I don't want to be wrong, but it's another power of epsilon. So it turns out that the balls in this metric space, the small balls become very flat. So it takes a lot of distance to go up, and compared to how much you go to the side. Okay.
But isn't this always the case when you have a contact structure?
That's kind of, it's a model of more general contact structures, yes. And these are all codimension 1. And then, but if you are so in this case, they prove that they are all lines. All the uniform measures are lines, right? It becomes very rigid in the case where it was studied. And I think it could be that doing more differential geometry for one-dimensional uniform measures in Heisenberg space of dimension general dimension, then maybe you could find something more richer structures. Yes.
Right. And the second question would be, can you elaborate a bit more? I'm very interested for other reasons in manifold learning. Right. So I've been looking into this problem, sort of differential geometric data science. Can you say where this business crops up in there?
I mean, it's a very let me put it this way. I would say that to study the geometry of measures, this is a case of studying the geometry of distributions of points in space, right? So we could be data sets, and then you want to, so for example, when people study manifold learning, you have a manifold, and then you have you say that this manifold is approximating your points, right? So there are people who study this in terms of rectifiability, of how far is how to construct this manifold corresponds to finding a subset of these points, so that the variance in the transverse direction is going much lower rate than so the distribution of points in the transverse direction is much lower, much less than in the parallel direction, right? So you have to quantify the convergence of the distribution of a measure to something flat. So if you know how to do that, then you can quantify so give a pass from local to global in measures of how these points are approximated by a manifold. Okay.
Cool.
But I think, well, I can look up papers. I looked from time ago some papers going in that direction. And then, so what I was saying is just that if you study geometry, like to study the geometry of measures is important in order to do quantification of this. And so, for example, if I look in my data set, all the points that are within a given distance from a data point, and I see that these, I mean, it will not happen in reality, but suppose I see that the growth of the number of points goes like very sharply, like r to the 3. Well, people will say, well, then it's a plane. Then you get something very well approximated by a plane. But no, because you could also be getting this other measure which has the same distribution, which is a cone, right? So this is how this classification can help to know, well, you have a black box, you have partial information, just how many points are involved. Well, what is the information about the measure that comes from it, about the support of the measure? So this is the kind of a basic question. Well, I'm not saying that it's going to be applied tomorrow, but I mean, it's still one fundamental question behind this study of data points as well, to find, given the distribution of the measure, how much I know about the geometry of the point.
Cool. Thanks.
That's what I meant here.
Have you got any more questions? No? We good? Okay, Mircea, thank you very much. Let's thank the speaker again, please.
Thank you for listening.
Thank you very much.
And Piccioni, the cat, was very pleased with your talk as well. All right, everyone. So we see each other. On Friday. Have a nice weekend. Bye.
See you. Bye.
Bye.
Bye, everyone.
Paulo, do you want to stay online for a second? Paulo, você quer ficar online um segundo?
Sure. Yes.
Então vamos falar de organização?
Vamos sim. Espera aí que eu boto... Você está me vendo?
Sim. E você a mim, eu suponho.
Espera aí.
Agora?
Estou tentando.